So I'm going to be discussing Euler's formula, and this states that the number of vertices plus the number of faces minus the number of edges on a polyhedron, which is a 3D shape like a cube or a square pyramid. The number of vertices plus the number of faces minus the number of edges is always going to equal 2. I'm going to have a couple examples right here. So take, for example, a cube. Let's start off with something easy. You have the number of faces. You have one face on the top, one on the bottom, one in the front, one in the back, and then one on each side. That's 6 total faces. The number of vertices or corners, you have 1, 2, 3, 4 on top and 4 on bottom. So that's 8 total vertices. And then you have the number of edges, there's 4 on top, 4 on bottom, and then you have 4 edges on the side. So that's 12 total edges. So when you take the number of vertices, 8 plus 6 faces, that's 14, minus 12 edges, you're going to get 2. So that proves how Euler's formula works. But I also have 2 other examples that show how it works with the square pyramid and the triangular pyramid. And right now I'm going to show you guys how it doesn't always work. For example, when you have a concave polyhedron, which looks a lot more complicated, but it's not that bad. So with the concave polyhedron, instead of a normal polyhedron, which would look like this, these are the same shapes basically, except this one's convex and this one's concave because the points go inside of the shape, and then here the edges or the points go outside of the shape. So with this concave polyhedron, I'm going to show you guys how Euler's formula doesn't always work. So we're going to start off with something easy, the number of faces. I have 5 triangles on the top, 5 triangles on the bottom, that's 10, and then I have 5 squares going around the side. So 10 triangles and 5 squares is going to be 15 faces total. And then we have the number of vertices. We have 5 on top, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5 on the bottom. And then we also have 1 vertex in here. If this was just a normal polyhedron or a convex polyhedron, you would have 2 on the outside, 1, 2 vertices. But since they meet in the middle, because it's a concave polyhedron, this vertex right here only counts as 1. So you're going to have 11 total vertices. And then the number of edges, we have 1, 2, 3, 4, 5 edges on top, 5 edges on bottom, that's 10. We have 5 edges around the sides, that's 15. And then you also have edges on the inside, which is where it gets a little bit more complicated. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more edges in the middle of the shape. So the total number of edges is 5, 10, 15, and then plus the 10 in the middle, it's going to be 25. So 25 total edges. And then to show how Euler's formula doesn't always work, you add the number of vertices plus the number of faces, which in this case, 11 plus 15, that's going to be 26. And then you subtract the number of edges, which is 25. And Euler's formula says that that after you add the number of vertices plus the number of faces minus the number of edges, you should get 2. But in this case, with the concave polyhedron, you end up with 1. So that shows how some shapes don't, or some polyhedrons don't work with Euler's formula.